Hello everyone. On this video we will look at how to find higher order derivatives using limit definitions. Alright, so far we know that our first derivative is equal to the limit of our function of f of x plus h minus f of x all over h as h approaches 0. Okay, so this is known as our first derivative. Okay, now if you have, let's say, f prime of a, then that's going to equal the limit as h approaches 0 of f of a plus h minus f of a all over h, or you can have the limit of f of x minus f of a all over x minus a as x approaches a. Now this is what we call your first derivative of a function at a fixed number that we will call a. All right, now a derivative can be denoted a couple of different ways. You have your first derivative can look like this, just f prime of x, same as we have up here. It can also be denoted as the derivative of f with respect to x. And that f can also be brought out front, so you have the derivative with respect to x of a function f. Again, this is your first derivative. Okay. Now your second derivative is really just the derivative of your first one. So your second derivative, that is denoted by the second derivative of f with respect to x. And like I said, really that's just the derivative of whatever your first derivative is. And this is your second derivative. Same thing with your third derivative. Your third derivative is just the derivative of your second derivative. Okay, so that's the third derivative of f with respect to x. And that's just the derivative of whatever your second derivative is. Okay, now you will see these little slash marks for the first, second, and third derivative. You could see them for the fourth derivative, but more than likely you won't. So for the fourth derivative and higher, you'll see just a little 4 in parentheses. Okay, and that's just the fourth derivative with respect to x. And that's just the derivative of your third derivative. And it goes on and on and on and so forth and so on. Okay, so it keeps up with that pattern. Alright, so if you are still writing, feel free to press pause. But I'm going to go ahead and finish it. When I finish it up, I'm going to go ahead and continue this on the next page. Okay. Now, when we have our initial function, move that over. There we go. Your initial function is known as your position function. All right. Now, the thing is, your initial function or your position function can look like numerous different ways. So you can have, let's say you can have f of x. You can have p of x. You can have r of t. You can have any number be your position function. Are all position functions. Okay. Now, if your position function, the one that's most likely used or more often used in story problems is s of t. And I'll just draw a line down the middle of my s. Is commonly used in, I'll say, word problems. Okay, where knowing the position function is necessary. Okay, now if we move on down to our first derivative, okay, so that could be the first derivative of our position function is known as your velocity function. Okay, and literally your velocity function is the first derivative of whatever your position function happens to be. So that means it could be, just going to write this under here. It could be f prime of x. It could be p prime of x. It could be r prime of t. Are all velocity functions. Okay, but just like up here, we have a certain variable that's used or a certain function notation that's used for most word problems. Okay, it's not always used, just commonly used. Okay, so you have your s prime of t, but your first derivative of your position function, they will call that your velocity function, so v of t. Or commonly denotes velocity functions. Okay, because I don't want to give you the impression that it's always. Commonly denotes velocity functions. Yep, there we go. Okay, now your second derivative, sorry about that. That is called the acceleration function. All right. Now, just like all of these, you might see it as the second derivative of x, or the second derivative of p, or the second derivative of r with respect to t. It could be with respect to t here, respect to t here. All these can change. Are all acceleration functions. But just like our position function and our velocity function, you do have common functions for your acceleration. Okay, so for your acceleration, that's the second derivative of your position function, which would be the first derivative of your velocity function. Okay, and that is denoted by A of t. Commonly denotes your acceleration function. Okay, and once again, these are common notations. It's not saying it's the only notation you will see, just what you will see most often. All right. Okay, so if you are still writing, feel free to press pause. Well, actually, we do have a little more room on this page, so I think I'll just continue on this one. Okay, now if you have your third derivative, it's called the jerk function. Okay. Now with the jerk function, there's no special A of t or V of t for it. It's just usually the third derivative. Okay, so that could be the third derivative with respect to x, the third derivative, let me clean that up a little. Respect to x, that could be r, and the third derivative with respect to t, or it could even be the third derivative of our position function with respect to t. All jerk functions. All right, so we have our position function, velocity function, which is our first derivative, our acceleration function, which is second derivative, and the jerk function, which is the third derivative. Okay, so now if you are still writing, feel free to press pause, but I'm going to give you a little more of an explanation as to why each of those are what they are. Excuse me. All right. Now, if you have your S of t, remember that's just your position. That's just your regular ordinary function. The same way as if you would say when x is equal something, what would my value be? Same thing here. When t is equal a certain value and you replace all the t's in the equation, then you know the position of your y value or your S of t. Okay, so this is the position of an object at time t. Okay, so it's just a regular ordinary graph. Now your velocity function, which is your first derivative, that's your velocity of a function. At time t. Okay, why is that? Because if you remember, your first derivative shows the rate of change. Okay, so we're looking at the rate of change of our position function at a specific time. Okay, so now what about our acceleration function? Remember, that's just the derivative of the velocity function. Oh, clean that up. Or the second derivative of our position function. Okay, so that's the acceleration of an object at time t. Okay, so if the first derivative shows rate of change, then if you take the derivative of the first derivative, ironically enough, that just shows the rate of change of the rate of change. Okay, so that's your acceleration function. How fast is the velocity changing? Is it changing from 5 miles an hour to 10 miles an hour? Then that's your acceleration. If it's going from 10 miles an hour to 5 miles an hour, then your acceleration would be negative. It's going down. Okay, so fourth would be the next one will be your third derivative, which is the derivative of your acceleration function, which is the second derivative of your velocity function, which is the third derivative of your position function. Okay, so those two are pretty much the same depending on what's being used to show your position function. And that third derivative is your jerk function. Okay, now since you have the derivative of the acceleration function, then your jerk function is really just the rate of change of your acceleration. Okay, so that's the main idea of your jerk function. All right. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and jump into a few examples. Okay, so for example, let's say if you have for f of x equals x to the fifth power, find f prime of x, your second derivative, your third derivative, and your fourth derivative. Okay, just a heads up, this is going to get a little bit lengthy, so you may want to start with a fresh sheet of paper. Okay, so to find our first derivative, we know that f prime of x is equal to the limit f of x plus h minus f of x all over h as h approaches 0. Okay, so we know that by definition. Okay, so what else do we know? We know that f of x equals x to the fifth power. So f of x plus h is equal to x plus h to the fifth power. Just replacing x with x plus h for both of them. Okay, so that's going to equal the limit as h approaches 0, our f of x plus h to the fifth power, minus our f of x, which is x to the fifth power, all over h, as h approaches 0. Okay, now x plus h to the fifth power, you can actually expand that using Pascal's triangle, or binomial theorem, whichever way you're comfortable with. Equals the limit as h approaches 0. So x plus h to the fifth power is equal to x to the fifth power plus 5x to the fourth power times h plus 10x to the third h squared plus 10x squared h to the third plus 5xh to the fourth plus h to the fifth minus f of x, so that's minus x to the fifth, all over h. Right, and conveniently enough, those two will cancel each other out. So that's going to equal the limit as h approaches 0. We're going to go ahead and factor an h out of every term in that numerator. So if we factor out that h, we have 5x to the fourth plus 10x to the third h plus 10x squared h squared plus 5xh to the third plus h to the fourth all over h. Okay, so by factoring an h out of each one of those terms, these two will cancel each other out. So we're just left with the limit as h approaches 0 of 5x to the fourth plus 10x to the third h plus 10x squared h plus 5xh to the third plus h to the fourth. So if we plug in h equals 0 using direct substitution, if h equals 0 for here, 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 and here, these all just disappear. There is no h to replace there. Okay, so we know that f prime of x is equal to 5x to the fourth power. Okay, that's our first one down. Okay, what about our second derivative? Well, remember, your second derivative is just the derivative of your first derivative. Okay, so let me go ahead and separate that. So your second derivative is going to equal the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h. Okay, so for your first derivative, it's the derivative of the function. For the second derivative, it's the derivative of the first derivative of the function. Okay, so we can see here that f prime of x equals 5x to the fourth power. So that means f prime of x plus h equals 5 times x plus h to the fourth power. Let me clean that up just a smidgen. There we go. Okay, so that's going to equal the limit as h approaches 0, f prime of x plus h is 5x plus h to the fourth power minus f prime of x, 5x to the fourth, all over h. Okay, so just like before, x plus h to the fourth power, using either Pascal's triangle or binomial theorem, your second derivative is equal to the limit as h approaches 0 of 5. Now x plus h to the fourth power will become x to the fourth power plus 4x to the third h plus 6x squared h squared plus 4xh to the third plus h to the fourth minus 5x to the fourth all over h. Alright, so now we have to get rid of these parentheses, so we go ahead and distribute that 5 to each of those terms. So that's going to equal the limit as h approaches 0. Move that up some. You have 5x to the fourth plus 20x to the third h plus 30x squared h squared plus 20x h to the third plus 5h to the fourth minus 5x to the fourth all over h. Right, and just like above, you can see here that those two will cancel each other out. So what we're going to do again is we're going to factor an h out of each of those terms that are left. So we have h, so you have 20x to the third plus 30x squared h plus 20x h squared plus 5h to the third all over h, where these two cancel each other out. Okay, so we are left with the limit as h approaches 0. Let's move that up. Here we go. Of 20x to the third plus 30x squared h plus 20x h squared plus 5h to the third. You can see here, using direct substitution, h equals 0, this, and this will all become 0. So that means our second derivative is just going to equal 20x to the third. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page and find our third derivative. Okay, so now for our third derivative, that's going to equal the limit as h approaches 0 of our second derivative. So it's the second derivative of x plus h minus the second derivative of x all over h. All right, so you can see from the previous page that our second derivative of f with respect to x is equal to 20x to the third. So that means our second derivative of x plus h is equal to 20 times x plus h to the third. Trying not to take up too much room here. Okay, so that's going to equal the limit as h approaches 0 of 20 times x plus h to the third minus your second derivative, which is 20x to the third all over h. Okay, so that's what we're starting with for our third derivative. Okay, so you have the limit as h approaches 0 of 20 times x plus h to the third power. And just like before, you can use Pascal's triangle, or you can use binomial theorem to expand x plus h to the third power. So you have x to the third plus 3x squared h plus 3xh squared plus h to the third minus your 20x to the third all over h. Okay, so once again, we want to get rid of those parentheses, so we're going to go ahead and distribute that 20 to each one of those terms. So that's going to equal the limit as h approaches 0, 20x to the third plus 60x squared h plus 60xh squared plus 20h to the third minus your 20x to the third all over h. Okay, and just like before, these two cancel each other out. So we're going to go ahead and factor an h out of each one of those terms up top. So if we factor out that h, leaves us with 60x squared plus 60xh plus 20h squared all over h, where those two will cancel each other out. Okay, so that's going to equal the limit as h approaches 0 of 60x squared plus 60xh plus 20h squared. Okay, and again, using direct substitution for each one of those terms, if you plug in h equals 0, this stays as 60x squared, but this becomes 0 and this becomes 0 because 0 times anything is 0. So you're left with 60x squared. So our third derivative equals 60x squared. Okay, so now let's go ahead and find our fourth derivative. Okay, so for your fourth derivative, that's just the derivative of your third derivative. So x plus h. Sorry about that. So the third derivative of x plus h minus third derivative of x all over h. Okay, so what do we know? Well, we know that your third derivative is 60x squared. So the third derivative, x plus h, is 60 times x plus h squared. Okay, so this is going to equal the limit as h approaches 0. The third derivative of f of x plus h is 60x plus h squared minus your third derivative of f, which is minus 60x squared all over h. All right, so we're going to go ahead and finish that down here. So your fourth derivative is equal to the limit as h approaches 0 of 60 times x plus h squared. So that's 60 times x plus h squared is just x squared plus 2xh plus h squared minus your 60x squared all over h. Okay, so just like before, we're going to go ahead and distribute our 60. That's the limit as h approaches 0. We have 60x squared plus 120xh plus 60h squared minus your 60x squared all over h. Okay, so we see that these two will cancel each other out. And once again, we're going to factor an h out of what didn't cancel out in the numerator. That's the limit as h approaches 0 of h times 120x plus 60h all over h, where these two cancel each other out. Okay, so that leaves us with the limit as h approaches 0 of 120x plus 60h. Where if we use direct substitution, replace h with 0, that's the one that disappears. So that's going to equal 120x. So our fourth derivative of f with respect to x is 120x. So it's a little lengthy, but as you see, it's just the same thing we've been doing with limits all along, just repeated over and over and over again. Okay, so it's really nothing new, just a little bit longer. All right, so if you are still writing, feel free to press pause. Let me clean up that 120 a little bit. If you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right, so for this example, what if we have an object whose velocity starting from rest is v of t is equal to 36 minus t squared. And we know that t is between 0 and 6. And that's where your velocity function is measured in meters per second. Okay, so we want to use this information to find the velocity and acceleration when t is equal to 3. All right, so to do this, we have to understand that v of t is our velocity function. And the derivative of our velocity function is our acceleration function. Okay. Now remember, we didn't start with our position function. If this was our position function, we would have had to take the second derivative to find the acceleration. But because we're starting with the velocity function, we only have to find one derivative past that of our velocity function to find our acceleration. Okay, so you want to be really careful with that. Okay. So we know that our acceleration function is equal to the derivative of our velocity function, which is the limit of v of t plus h minus v of t all over h as h approaches 0. Okay, so you notice it's the same that we've used before, only difference is you're using the v instead of the f of x plus h. You're using the t as your independent variable. Okay, so we know that our v of t is equal to 36 minus t squared. I'll move this over a little bit. Move that up. Okay, so v of t plus h is just replacing every t with t plus h. So that's 36 minus t plus h squared minus your velocity function, v of t. So that's minus 36 minus t squared all over h. Okay, so just like before, you want to get rid of all those parentheses and get all that stuff out the way. So you have 36 minus t plus h squared. So that's going to be minus t squared minus 2th minus h squared. Because remember, you're going to have minus t squared plus 2th plus h squared. Then you're going to distribute that negative. Okay, so that's minus, so if we go ahead and distribute that negative, that'll be minus 36 plus t squared all over h. Okay, so you can see there that the 36's and minus 36 cancels out. The minus t squared and plus t squared cancels out. So we're just left with those two terms up top. So we're going to go ahead and factor an h out of both of those. The limit as h approaches 0. You have h times negative 2t minus h all over h, where those two cancel out. Okay, so we have the limit as h approaches 0 of negative 2t minus h. So again, using direct substitution, our h disappears because you have the limit of h as h approaches 0 is just 0. Here, there is no h to replace, so that just stays as negative 2t. So our acceleration function is negative 2t. Okay, we're not done yet, but we're getting close. Okay, so if you're still writing, feel free to press pause. But we're going to go ahead and finish this up on the next page. Okay, so we know that our velocity is 36 minus t squared. And they want to know what's the velocity at t equals 3. So when t is equal to 3, v of 3 is equal to 36 minus 3 squared, which is just 36 minus 9, which is 27. So our velocity when t is equal to 3 is 27 meters per second. Okay, now what about our acceleration? Okay, we know that our acceleration function is equal to negative 2t. Again, we know that when t is equal to 3, that's going to equal negative 2 times 3. Just replacing the t with 3. Negative 2 times 3 is negative 6. So we know that our acceleration function at t equals 3 is negative 6 meters per second. All right. Now, quick note, since this is kind of jumping out. When the velocity and acceleration have opposite signs, okay, now in this case your velocity is positive, your acceleration is negative, then the speed of the object is either increasing or decreasing. Now in this case it's decreasing because you have a negative acceleration. In this case it is decreasing. It's just a little tidbit that I figured you might find interesting. All right, so hopefully after all of that writing, this made sense, and I will see you on the next video.